Under some realistic circumstances, Proxima B might be a more pleasant world. Regretfully, models indicate that the freezing off of volatile gases on the night side may make tidally locked planets' atmospheres vulnerable to abrupt collapse. People have speculated about what life might be like on other planets for a very long time. The most powerful telescope currently in use, the James Webb Space Telescope, JWST, has made it possible to finally investigate that question while studying Proxima Centauri, the star system that is nearest to Earth and barely 4 light-years distant. Researchers have observed some oddities coming from Proxima B, one of the planets in the system. The brightest minds in science have been perplexed by these abnormalities, known as artificial lights. However, what are they? Do these lights point to the possibility of sentient life on Earth? Come along as we discuss James Webb's potentially game-changing finding of city lights, which is alarming. As far as we know, there is only life on Earth. People have wondered whether there is life elsewhere in the universe ever since civilization began. The search for extraterrestrial intelligence, SETI, project was started in 1984 by American astronomers Jill Tarter and Thomas Pearson to conduct just such an interstellar search. The nonprofit's goal is to collect radio signals from space because, due to their longer wavelength, radio waves are more likely to be picked up by the 42 radio telescopes that comprise the rare Allen Telescope Array in the Cascade Mountains of California. But no authentic alien signal has been found in the last 30 years. After that, the successful launch of the JWST contributed in the investigation of a variety of new planets orbiting far-off stars. With its highly sensitive detectors and its position as the world's largest telescope, situated approximately 1 million miles from Earth, it holds great potential to make important discoveries. More than 4,000 exoplanets have been found orbiting other stars since the year 2000, when there were no known planets outside of our solar system. NASA estimates that there could be trillions of exoplanets in the cosmos. Alien plant life may contain the first indications of life outside our solar system. When the Galileo spacecraft, which was headed toward Jupiter, turned its instruments back toward Earth, it discovered a clear trace of plant life in the form of the vegetation red edge, VRE, biosignature, which is a combination of red and infrared light reflected by plants. For example, a planet like Earth with a jungle covering should produce a strong and discernible VRE signal. The VRE of distant, Earth-like planets in the habitable zone surrounding stars will be measured by JWST, and this data may reveal crucial indicators of life in the exoplanet's atmosphere. The JWST might be able to track sunlight as it enters a planet's atmosphere and crosses its star. Spectroscopy would then be used to find the missing wavelengths since the atmosphere's atoms and molecules absorb particular wavelengths, giving the JWST a unique fingerprint that it can identify. The composition of the atmosphere and the possibility of life may be ascertained using this technique. Planets the size of Earth and with atmospheres largely composed of carbon dioxide, nitrogen, and oxygen might support life. It can be possible to identify technological life by searching for components that aren't often present. For instance, aliens seeing Earth's atmosphere from a distance would probably note the presence of chlorofluorocarbons, CFCs, which are produced for use in cleaning supplies and refrigeration. CFCs in planetary atmospheres would be a blatant sign of civilization if the JWST discovered them. On the other hand, life on exoplanets may not be at all like life on Earth. Even earthly life forms might appear foreign at times, such as extremophiles, organisms that can survive in conditions where other living things would perish. This class of organisms, comprising mainly bacteria, is resistant to harsh environments, including temperatures as high as 250 degrees Fahrenheit and strong acids with pH values lower than 3. It might make sense to begin with planets similar to Earth as they have a higher probability of supporting life than worlds with extreme temperatures or acidic environments. It is possible for prime candidates to circle a stable star at temperatures high enough to support liquid water on their surfaces. Though golden G-type stars, like our Sun, are less numerous and usually have shorter lifetimes. Studying planets around red dwarf stars, which are more common than suns and have lower luminosities and temperatures, is more likely in our universe. This prolonged period of time permits the emergence of life and the evolution of complex life forms. The initial mission of JWST will focus on the TRAPPIST-1 planetary system, which is located about 40 light-years from Earth. It orbits a quiet red dwarf star that is home to 7 rocky planets the size of Earth. 3 of these planets may have liquid water on their surfaces because they are situated in the so-called habitable zone. The TRAPPIST-1 star emits brightness that is comparable to Earth's, despite having a smaller and cooler mass than our Sun. Proxima Centauri, a red dwarf star located 4.25 light-years from the Sun, offers the best potential for humanity to view city lights outside of the solar system. For life based on liquid water to exist, a planet must be 20 times closer to Proxima than it is to the Sun because it is around 600 times fainter than the Sun. A planet with 1.3 Earth masses was found by astronomers in August 2016 in this habitable zone, which resembles a Goldilocks zone where the light intensity is just right to melt water. Proxima B orbits Proxima Centauri, but since it is just 4.6 million miles away from its red dwarf star, it is probable that Proxima B is an airless, dead planet. Its atmosphere can be totally destroyed by the powerful solar winds it is exposed to due to its near orbit. Because of its relative proximity to the star, Proxima B does receive enough sunlight to have Earth-like temperatures and liquid water. It is believed that Proxima B is tidally locked, meaning that, like the Moon in relation to Earth, it always faces the same side toward the star. Proxima Centauri has a mass of roughly 18% that of the Sun and burns far less brightly than one might anticipate for a planet that is only 5% of Earth's Sun's distance from its star. Although Proxima B seems like a red-hot cinder, liquid water could exist there if the planet has an atmosphere to retain heat, as only 65% of Earth's solar radiation reaches there. The planet is not very conducive to life, though. It is most likely tidally locked, which means that it faces the star in the same direction at all times, creating perpetual day and night sides with notable temperature variations. Additionally, the planet is exposed to 100 times more high-energy radiation than Earth is, such as ultraviolet and X-ray light. Because Proxima B is so close to Proxima Centauri, it is also subjected to high-energy particle bombardment during star flare-ups. The conditions for life may not be good unless it has a shielding magnetic field like Earth's. Volcanic activity can restore our planet's atmosphere, while planets with strong magnetic fields are less likely to lose their atmosphere. We can't even speculate as to whether or not Proxima B has an atmosphere because we don't know anything about the planet's magnetic field strength or volcanic activity. We are curious to find out if Proxima B has a developed civilization, though, as an atmosphere requires the presence of seas, and the two combined require the existence of life. The night side, which would otherwise be too chilly and dark for acceptable habitation, may be lit and heated by energy produced by solar panels covering the day side. A race has begun to ascertain if Proxima B crosses the face of its star as viewed from Earth in response to its discovery. Scientists would be able to ascertain the planet's mass and size through these transits, which would allow them to evaluate the planet's density and confirm that it is composed primarily of rocks. This would also provide insight into the composition of those rocks. Starlight flowing through the planet's atmosphere during a transit may reveal information about the nature of the object. That being said, there is just a 1.5% chance that the orbit will align properly for scientists to see a transit. The tendency of the star to flare adds to the complexity. A rocky planet absorbs sunlight and re-emits it as infrared radiation due to stellar heat, according to Columbia University astronomer David Kipping. This makes the star challenging, but stars like Proxima Centauri emit a different kind of infrared radiation from rocky worlds. Moreover, the JWST was developed especially to investigate infrared light. Determining the planet's atmosphere is dependent on the infrared heat signature of Proxima B. In addition, the Hubble successor is well attuned to the infrared region of the spectrum, suggesting that city lights on Proxima's night side might be observed by the JWST, but at a much lower intensity than those in use now. If artificial illumination is limited to a frequency band that is 1,000 times narrower than the star's light, the JWST may be able to detect it. As Proxima B orbits its star, its day side might be extensively covered in solar panels that reflect starlight. Day and night are the same, with chilly nighttime lows coming after midday peaks. Whether or not the planet is made completely of bare rock, however, determines how much the temperature varies during the day. Heat is carried by the water and the atmosphere. Put another way, Proxima B's day side and night side temperatures will differ more if there is no atmosphere. In fact, we can determine the exact amount of black body radiation that should be there because the day side will radiate all of the energy it receives from Proxima Centauri as a black body. Conversely, the night side would resemble a frozen version of hell. Should the temperature? Since there is less of a difference between day and night, we can assume that there is an atmosphere. Conveniently, once Proxima B completes its cycle around the star, the JWST will only need 11.2 Earth days to measure the infrared radiation from its two faces. If Proxima B has an atmosphere, the next stage will be to examine its composition. Particularly, the presence of gases such as oxygen, water vapor, and methane may suggest the existence of livable conditions, if not real live organisms. But in order to do this, we have to do the extremely challenging task of successfully capturing starlight as it reflects off or passes through the planet's atmosphere. Since the JWST was not designed with the purpose of searching for extraterrestrial life in mind, it is limited to examining in detail a small number of the closest potentially habitable worlds. It is also restricted to monitoring variations in the atmospheric quantities of water vapor, carbon dioxide, and methane. The strongest indicator of life, unbonded oxygen, is something the JWST cannot detect. The extremely large telescope, which is expected to start operations in the middle of the 2020s, is one of the proposed ground-based observatories that will be able to perform a full atmospheric research, even though some mixes of these gases may reveal life. One of the substances that the JWST could be able to find is ozone. The data from the JWST may be useful for 10 years from now, if those telescopes remain in service. More potent space telescopes might use state-of-the-art methods to filter out the glaring brightness of a planet's parent star and expose sunlight reflected back from the planet itself. It would be like covering your eyes to see farther away. This could be accomplished by big external umbrella-shaped satellites or tiny interior masks in space telescopes of the future. It is significantly simpler to investigate light reflected off a planet once starlight has been suppressed. Regretfully, non-biological forces can also produce most of the gases released by terrestrial life. For instance, sunlight can cause photosynthesis, which is the process by which water molecules are changed into oxygen and hydrogen, while methane, a gas, is emitted by both volcanoes and cows. Astronomers will inevitably come across some false positives when looking for extraterrestrial life. Thus, in order to determine whether a planet of interest geology or atmospheric processes can mimic a biosignature and assist in excluding false positives, astronomers need to have a solid understanding of the world. The next round of planet research could yield the strong proof needed to prove that life exists. The initial data from the James Webb Space Telescope provides us with a sneak peek at the major breakthroughs that are yet to come. One of the most important unanswered problems in science is whether life exists elsewhere in the universe. Perhaps there is plenty of life in the universe, or perhaps we are all by ourselves, alone on a lonely planet far out in deep space. In either case, the final answer will probably need considerable philosophical or psychological changes among the participants. For decades, the hunt for extraterrestrial life has fascinated people, giving rise to a plethora of theories and myths. Technological advancements increase our grasp of the universe and open up new possibilities for life beyond Earth. In addition to improving our ability to find far-off planets, space telescopes like the James Webb enable in-depth examination of their atmospheres, which aids in the discovery of possible biosignatures by scientists. Furthermore, the study of exoplanets fosters cooperation amongst international scientific communities. International collaborations in space exploration promote resource pooling and knowledge exchange, raising the likelihood of important discoveries. Because results are frequently disseminated to a large audience, stimulating interest and imagination, these cooperative activities also serve to increase public interest in and participation with space exploration. Ultimately, thinking deeply about our existence is prompted by the philosophical ramifications of discovering life elsewhere. Would the finding of alien civilizations alter our perception of the meaning of life? These inquiries force us to reconsider our place in the cosmos and our connection to our home planet. Every new finding advances our understanding of the cosmos and helps us get closer to addressing the age-old question: are we alone in the universe? There is a lot of potential in the voyage ahead, which will propel the search for knowledge and understanding outside of our planet.